Here we're designing a high-pass digital filter. It's going to have a narrow stop band, and once we get an initial solution, we'll try to squeeze down the number of coefficients and still meet our specification. This is a problem put forward in a recent DSP forum where we're allowed between 64 and 128 coefficients for the FIR realization. Stop band is going to run DC to 0.025 in normalized terms. Passband then picks up at 0.05 and runs to Nyquist, giving us an allowed 0.025 transition width stretching between those two band edges. The ripple structure is not completely clear, although we are told to suppress to 50 dB. That's fine. For the stop band attenuation, it leaves open exactly how to interpret that for the passband. I'll show you a couple of interpretations. We'll be taking the Minimax pathway suggested in that forum. Up here in Slifer, we'll start with 64 coefficients. I'm typing in up in the upper right hand side, and in the hopes that we might get by with the smallest filter that we're allowed. And I'll tune down here to the Selesnik Minimax Highpass filter, which is an equal ripple type of filter I like quite a lot. Well, not in this case, of course, because it dives down to 0, as it must. The gain must be 0 at Nyquist for a linear phase FIR filter. So, in reality, I've got to bump this up to 65 coefficients, which cures that problem. And my allowed range really is 65 to 127. Odd numbers only. Well, this is the Selesnik filter. I can move the band edge, and this is the only thing I can control about the transition band, the exact point at which 0.5 gain is occurring. And otherwise I don't worry about the transition band. I'll let this come out in the wash, because what I control directly is the size of the ripple in the passband and in the stop band. This is the exact complement of what happens with Parks-McClellan algorithm, where you focus your attention on the transition width and the ripples come out in the wash. Well, the stop band attenuation I've said was 50. I'm going to make it 50.01 just to nudge it slightly over the line. You can see this flattens it out quite a lot. Passband, I have lots of possibilities. Let me just show you. I can control it and make it skinny or in quite big oscillations, whatever I like. My first interpretation is to say that they really want me to take 20 log 10 of the peak error, and I'll do this then by 50.01 for that as well, so that we have uniformity between these two parts of the specification. This makes it a very tough problem to meet, and as I dial this in closer, I've got to go to into my transition width. I've got to put this at 0.0375, which is bang in the middle of the transition allocated for this, between 0.025 and 0.05. Is it any good, this filter? Well, let's take a measurement with this quality measurement device, and while I'm at it, I'll set it up so that it automatically updates for any changes I make. And I'm seeing here mostly the passband. And I'm looking here and seeing that all well and good on the stop band attenuation, just as I specified, and just over the edge in the passband. There are other interpretations I could go for here. This is what I'm going for. And focusing most of my attention now in this middle panel, where I'm immediately shot down by the fact that this transition width is way too big. Could only be as big as 0.025, so I've had it. The only thing I can do is throw more coefficients at this problem. So I'll go to the other edge, 127, in the hopes that I can get a solution and work my way back down. Well, here's the transition width. Sure enough, it's not as big as 0.025, and furthermore, these two numbers are good. This is, I'm slightly above 0.025 here, I'm slightly below 0.05. So these are the three things I have to check each time. So this design is well in. In fact, I'm over the size I need. Let me try to go for 117 and see if that will still do the trick. Well, transition width is good. It should be 0.025 or less. I'm above 0.025 just barely. I'm below 0.05. So this is an acceptable solution as well. Let me go on down to 111. See if I can squeeze it that much. And I think I've really gone as far as I can go on the transition width because I'm right at 0.025. I'm okay here, I'm above, but I'm slightly above the upper edge. So I'm a little bit unhappy with this. I need to move this transition width down a little bit, which I can do by reducing the half frequency gain. So I'm going to just take it down a smidgen here. I'm going to go to 0.03745 and see what that does. Now check my measurements. Still, all this other stuff is still the same. And the transition width is just okay. And I'm just in, just below. So this is an acceptable solution. So I'm getting really close. Can I go to 109? See what will happen here. I see this right away. I've had it. Transition width now has gone too big. So I go back to this and I declare this to be my solution to this problem as I've interpreted the ripple structure, and those are my coefficients which I can export. Well, I'm aware that there's another solution put forward by a colleague who says it can be done with 75 coefficients. Well, that's true, but the interpretation of this passband has to be changed. As is often the case in MATLAB calls, the ripple is described in terms of something I'm going to change it to here, peak to peak ripple, and it's going to be measured in dB. Now, the specification the colleague tried was to put 1 for that peak to peak ripple, which you can see is massively bigger, and therefore the design problem is nowhere near as hard as before. In that case, well, I wonder if we can get by with 75 for the coefficients. So for this relaxed problem, I see that the width, transition width is okay. This edge is, oops, a bit low, not too good. Otherwise, if I can bump this back up somewhere, then I'll be probably in. So I do this by going down here to a nice number of 0.041. Check this. Still, everything is okay on the outliers here. 0.022. Now I'm just above, just below. So this is now I've met this other solution that we heard about. Can I go even better? I don't know. Let's go down to 73 and see if it still holds up. And sure enough, transition width, I'm above, I'm below. Okay, can I go better? 71. Well, not really. I'm just a little bit low here, so I'd have to nudge this up. So there's serious small amount of nudging because the 0.025 is still not being exceeded. Very close though. So I'm going to go back down and say that 73 coefficients of this for this reduced solution is what I'm going for. Now, why do we struggle so much to lop off a few coefficients? Sometimes it's very important to make your filter fit on a pre-allocated board structure, or maybe you have harsh requirements on your software timing so that the number of coefficients can really matter down to 1 or 2 coefficients. So here's how we've done this solution pretty easy.